Okay, then I'm going to turn the mic over to Mark Skoog, and he's going to tell you about our flying program that we have now.
Thank you, Leslie. Well, as I said, I'm Mark Skoog, and unlike many other folks that you have seen up here today speaking, I am not a pilot. I'm an engineer by choice and a project manager by need. I enjoy doing widgets and gadgets, as you'll see as we get into this program. What I'm going to talk about is automatic collision avoidance. Initially, we started working on the F-16 for the Department of Defense, sponsored by the Secretary of Defense. And in the fighter community alone, on the Air Force side, there is generally about 1 to 2 aircraft lost each year at a rate of around $100 million in hardware being lost with no dollar associated with those folks. In the general aviation community, aircraft purely flying into the ground, there's roughly 100 lives lost every single year within general aviation. These are some of the areas that we're trying to target and eliminate, if at all possible, those fatalities, making aviation that much safer. I'll talk first about the F-16 program, which we finished up about 1.5 years ago, and then I'll move on to the DROID effort, the small UAV effort that the aircraft is right over here. The F-16 program was a 103 flight program, 141 flight hours, which is a very large program. At any measure from a flight test perspective, that's a large program, shy of something that would be a major platform development such as the F-22, the F-35, or the B-2. But from a research perspective, it was an extremely large project. Our intent was to develop a system that would not only apply to the F-16, but would apply to all fighters. And in fact, we were trying to develop a system that would apply to any aircraft and be easy to adapt to it. Within aviation, technology is developed in what's called a very stovepiped fashion. It tends to be tailored directly for that aircraft. And when you want to put the same system on another aircraft, you almost have to repeat all that same development again to get it applied to that aircraft. That ends up costing a lot of dollars, and what causes a lot of the time to develop systems onto aircraft. You may have heard how long it takes to get research into the field. What we wanted to do here was to develop a capability that would go cross-platform, and it would be easy to adapt. A case in point as to why this problem exists today, aircraft have been running into the ground since the dawn of time. The Wright brothers had a problem with it. One of the brothers was severely injured in an accident where he ran right into the ground. And as an advent of that, seat belts were developed for aircraft. He just fell out of the aircraft as it was hitting the ground. And he was never able to fly again. I forget whether it was Orville or Wilbur. In the F-16 alone, there are no fewer than 6 different systems that try to warn the pilot that the ground's about to reach up and grab him. Yet, over the 30 years of those being put onto the aircraft one after another, there's been no statistical change in the mishap rates due to an F-16 running into the ground, a perfectly healthy F-16 running into the ground. Well, the reason is, as it turns out, when you take into account the fact that F-16 missions fly very close to the ground, and you need to account for a pilot's reaction time, especially one that may not be aware he's about to hit the ground, you have to warn him a fair bit in advance, about 3 or 4 seconds in advance of actually hitting the ground. Well, when a pilot's aware and flying around very close to the ground, he's got those warnings coming off all the time. Even though he's not going to really hit the ground, but the system has to assume the worst case, and he's going to do the wrong thing and hit the ground. Well, if you've had warning lights going off in your car and then take it into the dealer and find out everything's fine with it, it's just the indicator, after about 3 or 4 false warnings, the pilot tunes out the system or turns it off. And therefore, the one time that it's needed to be used, it has no effect, he doesn't react to it. And that's why those systems hadn't been working. So what we do with the automatic system is we model the aircraft very precisely as to how it can perform to avoid the ground. we model the ground very precisely as to what's out in front of him, and then we eliminate all reaction time by performing the maneuver automatically. So it can wait till the very last instant to actually activate, and it's not coming on as a nuisance as a result for the pilot. At the end of this presentation, I'll show a little video that will go through a series of clips showing our testing. One of the problems that everyone has had is focusing on collision avoidance, avoiding hitting the ground. They didn't take into account the fact of nuisance and the fact that the pilot will turn the system off and not use it. Just like if you're out there flying your model aircraft, wanting to do loops within about 50 feet of the ground, if the system's coming on, keeping you from doing your loop, you're going to shut it off so you can do your loops just fine. So the same problem exists in real aircraft. We've eliminated that, but we also focus very much on making sure it's nuisance free. So what you'll see in the video that I'll show at the end here is a bunch of very low level flying, very aggressive, and the system's not coming on. It's active when that's going on. So with that, and you can see a number of photos here in this picture, on this slide here, of us flying very low to the ground and it not coming on. We've had a number of different awards for this program, national awards. It's been very well received by the community. As we speak, in the next month or so, it's going to be finishing the production flight test on the F-16, and it should get fielded in about a year. So this is a case where we finished the research only about a year ago, and it should get fielded in about another year from now, which is actually record-breaking from getting a technology from research to the actual user. It should begin saving lives at about the late 2013, early 2014 time frame. It'll then follow on to the F-22 and F-35. Okay, so we did the F-16 program. The F-16 is moving on to do air collision avoidance, avoiding other aircraft, and that's what's going to be happening on the F-16 in a little over a year. In the meantime, I went back to the Secretary of Defense and said, we've said this could work on any aircraft, and granted it's going off onto all the various fighters, which is a little bit novel, but we need to look at an aircraft that's very different. These are all fighters that we were talking about. So they said, fine, why don't you go ahead and put together a low-scale program to show it on a very different aircraft, and that's where the DROID came in. We took the small UAV that we've got, we limit its climb performance to about 1,000 feet per minute, which is pretty common to most general aviation aircraft, and we showed how we could tailor the system to that performance as opposed to the F-16's performance. Also, because we're dealing with a very tiny aircraft, we had to miniaturize all of the hardware. So we decided to go ahead and make it a cell phone app, and we're running it on an Android cell phone. Got the app right here on this phone, and you'll see if you look inside the fuselage of the airplane there, you'll see the phone mounted inside of it. Now all we're using the phone for is the computer inside. We don't use the cell phone part of it at all. We don't need a cell phone tower, we don't make any calls. We're just using the computer that's inside of it and the memory storage device. The other problem is we need to know what the terrain is, and if you use an active sensor to ping the ground, that costs a lot of money, it adds a lot of weight. So instead we use a computer model of the world. This computer model has what the elevation of the terrain is in about a 100-foot by 100-foot grid across the entire globe. Now the F-16 doesn't have enough memory space to store the entire world. It only does about a 400 square mile area roughly. We carry the entire world, the entire globe on this phone because we developed some special software utilities to compress the entire globe onto the phone. So we can go anywhere in the world with that little UAV and turn it on and it'll avoid the ground. The F-16, the pilot has to do some pre-mission planning to load the data on for whatever area he's going to fly on. So we went ahead and did that. Also in the process of doing the program, we found some interesting limitations to lower performing aircraft that the algorithm didn't support. And so we had to add some new features to the system that were above and beyond what the F-16 can do. So we look at multiple escape trajectories, a left and right chandelle, if you're familiar with that maneuver from an aviation term, which are a climbing turn, as well as a straight climb over the terrain. And we look to see which one is the most efficient to avoid the computer model of the world we're sharing. We also use the GPS on board the aircraft to figure out where it is so we can position it over that computer model of the world. And with that, we make the system work. Here's an example of some of the algorithm going on. The left and right escape trajectories there on the left-hand side of the, as well as the straight recovery, although it's a pretty severe turn. It turns because of the high P factor. The prop puts on a turning moment that when it's in a wings level climb, it actually causes it to turn. We have to model all of that, so the computer model of the aircraft running in the phone models that all those aerodynamic effects that are going on the aircraft. We also have a high fidelity computer model. It's kind of illustrated on the right there of the digital world. We bring it all together. Victor showed some of the pictures of the cockpit system. The phone there is in the lower left. When we run it on the ground, we interface it through another laptop that allows us to control the system. That then talks to the normal computer systems that operate the aircraft in an unmanned aircraft fashion. That laptop on the right of the cockpit is the standard computer that runs it in a UAV mode. That all then gets communicated up and down to the aircraft through that box on the right, up to the aircraft there, to the autopilot that you see pictured in the upper left of the slide. We also have to have a lot of people supporting this from a safety perspective, because we don't know that this is going to work for sure, and we don't want to lose our aircraft. So we'll have a safety observer, number of safety observers out in the area where we're doing the actual runs, and Leslie will act as our safety pilot. She's out in the field. I send her out into some pretty remote places to take over the aircraft should she need to. When we move the phone on board the aircraft, it just mainly goes back up on the aircraft. The phone's a little bit more contemporary than the autopilot we have. The autopilot's getting a little bit old, so it doesn't speak in the same language that the phone does, so we have to have a little tiny gumstick computer in between the two that can translate the phone's language into the autopilot's language. We go out to some pretty remote sites. Where we do most of our testing is about 30 miles northeast of the intersection of Highway 395 and Highway 58, if you're familiar with that area. It's about halfway between Mojave and Barstow. We use that area for our extreme mountain testing. You see a picture of the terrain there on the lower part of the screen. As I said, the map we're using is the whole globe, and we originally developed this for use on the F-22, and we're actually running the F-22's map on here. The F-22 has yet to even begin their core design development, so they're very anxious to see the flight test results out of this small UAV effort as well. So we're using this high-end, hobby-grade model aircraft to do some very leading-edge research. All in all, it's a pretty small aircraft, but it takes an awful lot of people to do these tests. You see the line of cars there for all the people getting out to some of the sites to support the tests. We have the phone sitting in the lower left there. We have a person sitting at the laptop that controls it. To his right is the person acting like the UAV operator, working through his computer system. To the right of that, we can have a pilot. The pilot's optional. We have people to monitor the data that we're recording when we do these flights, as well as a test conductor to make sure everything gets orchestrated. And then we have Leslie and other ground observers out in the field, close to where the aircraft's actually going to fly at the ground. And then it all comes together for our tests.